This lesson is on complex numbers, and before I explain what complex numbers are, I want to do a brief review of all the other number sets that you might have come across previously. So we'll start with natural numbers. So natural numbers, N for short, and we know that they are the counting numbers 1, 2, 3, 4, etc. So they're the natural numbers. After that we have the integers, or Z for short. And of course the difference here is we still include the natural numbers, but now for the first time we're including the 0, -1, -2, etc. So it goes on forever in both directions. Next we have the rational numbers. They're called Q for short. And the clue is in the name ratio. So they can be expressed as a simple ratio. For example, a half, 3/4, 6/5, minus a half, etc. And again, it goes on forever in both directions. Generally speaking, their numbers can be written as an integer over an integer, so as a simple ratio. We don't include 0 over 0, but apart from that, they are expressed as an integer over an integer. Okay, moving on from there, we have the real numbers. Now, the real are defined as the rationals, all the rationals so far, everything so far basically, plus the irrationals. And when I say rationals, and what I mean by everything so far is this as well, we can't forget, of course, the rationals, simple ratios. That would include all previous numbers, because, for example, a number like 4 can be written as 4 over 1, or -2 is -2 over 1. So the rationals includes everything so far. Therefore, the reals includes the rationals, which is everything so far, plus a new set now called the irrational numbers. So what are the irrational numbers? Well, they are numbers like, for example, √2 or √3, numbers that cannot be written as a simple ratio. I mean, you can write them as √2 over 1, that's a ratio, but it's not a simple ratio in terms of an integer over an integer. So, or you can write them as, for example, pi. Other examples of irrationals are pi. Pi is, it's 3.142, goes on forever, but you can never write it as a simple fraction. And E, these constants you come across in your maths course, pi and D, that are built into nature really, these would be other examples of irrationals. So they are all the number sets so far, and we can show them more visually in a Venn diagram format. So what you can do is you can, for example, there's the natural numbers. That's a set of numbers, but then the integers includes all of those, plus it adds on the minuses and the 0, etc. So 0, -1, -2, etc. So that would be 1, 2, 3 would belong in there. So this is the integers. And then we have another set around that. We have the rationals, which are Q for short. So now we're including for the first time things like a half, 3/4, 6/5, -1/3, etc. And then, of course, we have the real numbers. So the real numbers are R for short. Now we're including for the first time things like pi, E, √2, √3, etc. So there's your Venn diagram representing all the number sets and how they're related. Now, so that means that every number is a real number. Every number so far is a real number, because they're all subsets of the real numbers. And that means we can draw a real number line. And we can show every number in its place on the real number line. So if you draw a real number line, we call it RE there for short, so RE. And there's 0, there's 1, there's 2, 3, 4, etc. -1, -2, -3. Well, we have numbers like, even the most complicated numbers like pi, which we can't write as a simple ratio. We don't know exactly what it is because 3.14 was on forever, but we do know it's in there someplace. I mean, it's 3.14 something, so it belongs there on the real number line. The same for √2, for example. √2 is 1.4 something, so again, it's roughly in here. So even the most irrational of numbers can be shown. They still have their place on the real number line alongside all the simpler type numbers. Now, that leads us on to a new type of number that we haven't come across before. And that number, we come across it for the first time when we try and solve the following. If you have this equation, I squared equals minus 1. What's I is the question. Try and think of a number when you square it, you get minus 1. So we'll just say this is the question mark from now on. What about? What about I squared equals minus 1? Well, what is I? Let's try something first. Try minus 1. So minus 1 squared, minus 1 by minus 1 is plus 1. That doesn't give it. So if I was minus 1, that wouldn't be the answer because minus by minus is still plus. And you could be trying all you like, but you'll never get an answer for this puzzle, basically. Something squared is minus 1. What is the something? There is no number. I mean, if that was, for example, something squared is 9, you'd have that something. It could be 3. 3 squared is 9, or it could be minus 3. So there is no answer to this. And for that reason, we call it an imaginary number, because we can't imagine anything that solves that equation. So I is basically what's called an imaginary number. Now, if I is an imaginary number and we can't visualize what it is because there is no answer to this puzzle, the next problem is if we're going to accept that it's some kind of a number, it's imaginary, where does it fit on the real number line? And the answer is simply it doesn't fit because we can't even work out what it is. So if we can't work out what it is, we don't even know where it fits in relative to the other numbers. So now we've got a new problem. Now, where do we put it? If we want to represent it visually like all these other numbers on a line. And the answer is we can't put it on the real number line. It doesn't belong there. So we have to create a separate line to represent this strange number I. And what we do is we draw another line perpendicular to the first axis, and we call it the imaginary axis through 0. And we put I on that separate axis. So that's what the next step is. And so what we can do now is we just draw an X and a Y axis. So it's similar to your X and Y axis that we had before in coordinate geometry. The difference is what they represent this time. The X axis now represents the real number line. And now we've also got an imaginary number line. So for example, 1, 2, 3 would be along there as normal, minus 1, minus 2, minus 3. Of course, it goes on forever in both directions, the real number line, as does the imaginary number line now. So now for the first time we have this number I, as we said. So there it is. And we don't know what it is, but here's the great thing about maths, we can work around it. If that's I, well, whatever I is, that must be 2I, the next spot up there. And if that's 2I and that's I and this is 0, well, this must be minus I. And this must be minus 2I, etc. And that's what's called an Argon diagram. There's a name for this diagram. It's called an Argon diagram. So there's your Argon diagram. So there are an infinite number of real numbers on the real number line. There are an infinite number of imaginary numbers on the imaginary number line. And it doesn't even stop there, because now you can imagine other numbers, number types like this, for example. If I dot in this point on the plane here, I can now imagine another number, 3 along the real number line, plus 2I along the imaginary number line. And so we can imagine a number which is a combination of the two, which is 3 plus 2I. And we can give it a name. They often, in the books or in the exam papers, they call a number like this a Z. So Z is 3 plus 2I. And we can build up a whole set of numbers again like that. So for example, down here, you might have minus 2 minus I, for example. So that's minus 2 minus I. So that's Z equals minus 2 minus I. And it goes on like that. And now what we have are what are called complex numbers. So these are the complex numbers. Whenever you have a real part and an imaginary part like that, well, the combination is called a complex number. So here's your complex number. That's what a complex number is. When you have a real part and imaginary part together there, and you can plot it on an Argon diagram, that is what's called a complex number. So we have a completely new set of numbers now called the complex numbers. So we had the natural numbers, we had the integers, we had the rational numbers, we had the real numbers. Well, now for the first time we have the complex numbers as well. And they're a bigger set again. And all the other sets are now going to become a subset of the complex numbers. Because if a complex number by definition is any number you can write as a real part plus an imaginary part, well, every number so far belongs as well, because if you think about it, a number like, for example, a simple number like number 2, for example, can be written as 2 plus 0i. Or a number like -3 can be written as -3 plus i plus 0i, for example. So they all fit the definition. Every number so far still fits the definition of a complex number. And, q a half plus 0i, root 2 plus 0i, and finally, the numbers themselves, the complex numbers, 4 plus 3i, for example, or -2 plus 6i. And it turns out that the complex numbers are the last set of numbers to be discovered. There are no other sets beyond the complex numbers. There's even a whole theorem that proves that. So every number that exists is a complex number, and we have now got the full set when we talk about the complex numbers. So a complex number from all that basically is the following. It's a number you can write as something, a real part plus an imaginary part, where A and B are real numbers. So an element of the real number set. So, and I squared, of course, is -1. So that's your definition of a complex number, what a complex number is. Now, with all that in mind, we can do an exam question based on what we've just done. So, for example, if we look at the 2012 exam paper, so let's have a quick look at the diagram here. We can see straight away we've got the integers z, we've got the rationals q, the real numbers. So we've talked about all of those so far. They don't show the natural numbers here. And there's the complex numbers. It's drawn as a rectangle, we should say as well, of course, because it's what's called the universal set. It includes everything. So that's the symbol for universal set in Venn diagram notation. Now, so everything here is similar to what we've done so far, except of course there's this other bit g. There's a new set here he calls g, but he defines what g is very clearly for us. G is a set of numbers x plus yi, where x and y are integers. Now, bear in mind for us the definition of a complex number is x is a plus b, where a and b are real numbers. So g is a bit more strict. He's not allowing real numbers in our complex set here. He's only allowing integers, whole numbers basically. So for example, in g you could have a number like 3 plus 4i, because 3 and 4 are both integers. But you couldn't have, for example, a half plus 6i. You couldn't have that. That would belong out here. So that's what he means by that. So he's got a new set g which only allows whole numbers. Okay, so with that in mind, let's do part A and B. It turns out part B is easier to do, because if you do part B in this one, A just falls into place. Insert each of the following numbers in its correct region on the diagram. So the root of 2, for example, would be a rational number. Sorry, irrational number. So it belongs out here in the irrational section. And it's in the real numbers, but not in the rationals queue. The number 7, well, we might think of putting 7 in the integers. The thing though is 7 could also be written as 7 plus 0i. And then that's more correct, because now it's in the intersection of g and z. So in there, it belongs in the integers, obviously, because 7 is 7. But it also belongs in G because these are two whole numbers now, 7 and 0. And it's in complex form, so it also belongs in G. It's in the intersection of the two. So that's a tricky one, the 7. Now, root 2 minus I, this one here. Well, you could try it here first, root 2 minus I, but it doesn't work because G, according to our definition at the very start, G has to have whole numbers. X and Y have to be whole numbers. And this X part here clearly is not a whole number. It's root 3. So they don't belong, that doesn't belong there. It belongs out here. 4 plus 3i, the next one. 4 plus 3i belongs in, it actually does belong in here because both numbers are whole numbers, 4 and 3, so it's fine in there. A half. Well, a half it's not an integer, obviously, so it doesn't go in there, but it does go in here. It's irrational. So keyword irrationals are ratios. Now, why doesn't it go in this section over here, for example? Why is it not part of the intersection with G? Well, again, G only allows whole numbers. And finally, a half plus 2i. Well, that would belong out here, a half plus 2i, because again, it's not a whole number, the half, so it has to belong out there. And that's them all done. Now, that makes part A very easy, because part A says there are 3 regions in the diagram that represent empty sets. One is already shaded, so we can see that. So we can't have a number in here. Because if you think about it, if you try to put the half in there, for example, it doesn't fit the definition of G. Now, the same goes for here, this region here, because anything you think of, any number you think of, say 7 or 8 or 9, it can also always be written as plus 0i, which shoves it in over here to the intersection. So there is no number that just belongs here only, in this little piece here. So we shade that in. So that's the other area. There is no number that can just fit in that part only. Now, similarly, there is no number that fits in, this is the only part left anyway, there is no number that fits in this part. Because if you shove the root 2 over here, for example, it doesn't fit the description for G. So therefore we can't conceive of any number that would belong in that section. So yet again, that is another section where we can't have a number. So this section here. So they are the regions that you've got to shade in to get full marks. And that's the end of this section on complex numbers.